Hello, everybody. Today's goal is to go over the materials we have learned since exam 2. I'm going to provide a list of knowledge points and also some questions for you to do a quick self-test. All right, so the first part is on the structures. In this part, the important things to know are the nomenclatures, how to name the common ligands, including monodentate ligands and polydentate ligands. This is including chloro, bromo, fluoro, aqua, amine, and the list of polydentate ligands that I showed in the lecture. Um, and on top of that, you should know how to name coordination complexes. There are a number of things you should pay attention to. For example, anions are named differently compared to cations. There are two different ways to identify the charge state of the complex. The Roman numerals can be used to identify the charge state of the transition metal complex directly, or you can use Arabic numbers to indicate the overall charge of the complex. And then there are different kinds of prefixes for different ligand stereochemistry, or the number of ligands in the complex. We also have done exercise to identify different stereoisomers, including chiroisomers. So those are mostly for octahedral complexes, but you should be able to do the same thing for TD complexes, ML4, or square planar complexes. Okay. So below I show three complexes. I'd like you to pause the video for a moment and see if you can write down their name correctly. Okay. So you can pause the video now, and once you finish writing their names, you can resume the video. All right, pause. Okay, so here are the correct names. See if you get all of them correct. If not, then you should go back and revisit the rules for naming those complexes. On the second part, we discussed bonding. Here, the important knowledge points are MO diagrams for both OH and TD complexes. And here you should be able to derive the MO diagram from scratch. There are different scenarios we discussed in class. For example, what would the diagram look like if you only consider d orbital interacting with sigma bond of a sigma donor ligand? What happens if you introduce the s and p orbitals on the metal? And what happens if you introduce pi bonding on the ligands? For the case of pi bonding, there are two different scenarios again. So there's empty pi orbitals on the ligand, or there's filled pi orbitals on the ligand. And in one case, you push down T2G levels. In another case, you push up T2G levels. Make sure you understand which case is which. Once you derived the MO diagram, you should be able to fill the energy levels with the correct number of electrons. And for this part, you should be able to correctly calculate the number of d electrons in the transition metal ions. We briefly went through this in the class. Basically, you look at the location of the metal ion in the periodic table. You take their column number and subtract that number by the number of positive charges in the metal ion. Okay. Once you have done that, then you should also predict, based on the nature of the metal ion and the nature of the ligand, whether the complex is likely high spin or likely low spin, and based on prediction to fill in the electrons in the correct way. Okay, so for low spin, you want to populate as many electrons as possible in the T2G level before you go to EG star level. For the high spin, you want to put as many electrons in the same spin direction as possible in all the d orbitals before you put two electrons in the same orbital. In either way, you should be able to calculate ligand field stabilization energy. Again, there are two different scenarios. OH is completely the opposite of TD. OH has non-bonding being T2G. There are three d orbitals there, and EG star having two levels being antibonding. Okay. For TD, the configuration is the opposite. The non-bonding has two orbitals and antibonding has three. Okay, so for those two different cases, the ligand field stabilization energies contributions are different. Okay, so make sure you figure out the correct value for each situation. All right, the last part is Young-Taylor effect. For this part, you should understand why Young-Taylor effect occurs. Basically, it's due to uneven electron population occupation on either T2G or EG star levels. And you should also understand what happens if you distort the structure of coordination complex, how that distortion impacts the levels of the MO diagrams. Okay. All right, so for this part, you can do a quick self-test by considering the following. So first of all, you can derive a generic MO diagram for iron complex, let's say iron hexacyano 4 minus. And once you derive the MO diagram, you start with the simplest possible. So on the metal, you have only d orbitals. On the ligand, you only consider sigma bonding. And once you finish that, you can introduce S and P orbitals on the metal, and then introduce pi orbitals on the ligand, and derive the MO diagram again, and identify what happens to the splitting between the d orbitals. And once you have done that, then you can fill in the correct number of electrons and make a prediction whether this is high spin or low spin. Once you have done that, calculate ligand field stabilization energy, and finally predict if Young-Taylor distortion is likely to occur for this particular complex. For the third part, we discussed term symbols. Here, the important technique is to be able to derive term symbols from the scratch. So what you should be able to do is to construct the table of all the microstates and fill in the table with the correct number of microstates. And once you have done that, to assign a collection of microstates to specific term symbols. And here you should pay attention to the nature of the microstates, because electrons are indistinguishable from each other. So if you have a microstate where two electrons having the same set of quantum numbers, then you should discard those duplicated microstates, because they are essentially the same thing. All right. Once you have figured out the term symbols, you should be able to identify the ground states for free ions. Here you should remember the basic rules. There's three. The first one says that you should identify this term symbol that has the highest multiplicity. And if multiple states have the same multiplicity, then you should identify the term symbol that has the largest capital L. If J is involved, then there are two scenarios. For system that is less than half-filled, there's one rule, and for system that is more than half-filled, there's a different rule. Okay, so I leave that to you to figure out exactly what rule applies to what scenario. So that gives you a way to identify ground state for free ions. On the complex side, so that is a case where you consider only ligand-metal interaction, but not electron-electron interaction. For that case, you should also be able to identify the ground state electronic configuration and also first and second, third excited states configurations. Once you can do that, then you should be able to read Tanabe-Sugano diagram. Here, I do not expect you to derive complex diagrams, maybe some simple diagrams, for example, D1. Okay? We did that in class. But anything larger than D1 is too complicated to be derived in the exam setting. But I do expect you to be able to read those diagrams, understand what those lines mean in those diagrams, and how to identify allowed optical transitions. So here you should understand what the selection rules are. Once you can identify allowed optical transitions, you can use those information to assign peaks in the UV spectrum and basically to explain what the peaks in the UV spectrum corresponds to in the Tanabe-Sugano diagram. For here, a quick self-test would be the following. You can pause the video and start to derive the term symbol for a P2 system. You have to construct the whole table. Fill in the table with all the microstates, and then assign the microstates to term symbols, and then identify a ground state for that system. Okay. Next, you should go to the text, or you can go back to the handout I gave in the class that lists all the Tanabe-Sugano diagrams for D2 to D8 ions. And for each one of the diagrams, I'd like you to look at them and identify what are the allowed optical transitions are, and then use those information to explain the UV spectrum of the first row hydrated transition metal ions that you can also find in the text. For the last part, we discussed reaction and mechanisms. Here you should understand the concept of inert versus labile ions. Here, those concepts are related to the ligand field activation energy. So again, you should understand what those ligand field activation energies are, what ions, basically what d electron configurations are inert, and what d configurations are labile based on the prediction of ligand field activation energy. There are two mechanisms of ligand displacement that we discussed in class, associative versus dissociative. And for both cases, you should understand what are the elementary reaction steps and what are the experimental characteristics associated with each of the mechanisms. And for both cases, you should be able to apply steady state approximation to derive a rate expression. And finally, for platinum square planar complexes, you should be able to use trans effect to predict the outcome of ligand displacement reactions. Okay. So here a self-test would be the following. You can derive a generic rate expression. So without looking at your notes and the text, see if you can derive the rate expressions for associative and dissociative mechanisms by applying steady state approximation. And then look at the periodic table and look at the first row transition metal ions and predict whether those ions, all the way from vanadium to zinc, whether their common ions are inert or labile. So that's pretty much what I want to discuss. If you have any questions between now and the exam, feel free to email me. I will also be available Tuesday afternoon, so if you want to stop by, happy to answer additional questions and go over go over them with you together. Thank you.